Welcome to Wireless Fundamentals, Session 5, Infrastructure and Architecture. This session is focused on understanding WLAN infrastructure components. This includes access points, wireless access controllers, and AP connectivity. We will also compare and contrast the different methods that WLAN systems can use to forward frames, including distributed and centralized forwarding. There are two basic modes of operation for APs. Fat APs are also known as standalone or autonomous APs. Each AP is managed individually via its own CLI or GUI interface. This is similar to how each individual Ethernet switch has its own user interface. Each AP is an autonomous device that is completely responsible for all WLAN functions. It must transmit frames from the wired network to wireless clients, and it must receive wireless frames from clients. When it receives these frames, it must figure out what to do with them. Most likely, this involves converting the frame from an 802.11 wireless format to an Ethernet format, and then sending the frame to the endpoint's default gateway. FIT APs are also known as controlled or controller-based APs. All APs are centrally managed by one or more wireless access controllers, or ACs. Wireless functionality is then split between the controller and its APs. The AP must transmit and receive wireless frames, as with Fat APs, but it does this based on configurations and commands it receives from the controller. HP's MSM controller series offers a cost-effective, high-performance solution for the mid-size enterprise campus. This solution supports all current standards while offering comprehensive security, threat protection, and high-availability features. The MSM 720 supports from 10 to 40 APs and 250 concurrent clients. Up to 2 controllers can be teamed together for redundancy. The MSM 760 supports up to 200 APs per controller. However, you can team up to 5 controllers to control up to 800 APs for increased scalability and redundancy. The MSM 765 and 775ZL are modules that can be installed into 5400ZL or 8200ZL series switches. They have similar specifications to the MSM 760, with up to 200 APs per controller and 800 APs for a 5-controller team. HP's Unified WLAN Controller series offers a cost-effective, high-performance solution for the mid-size to large-scale deployments, with over 200 APs and up to 20,000 clients. This solution supports next-generation standards such as 802.11a, b, g, n, and 802.11ac, with Wi-Fi Clear Connect integrated intrusion detection system, interference mitigation, and RF optimization. These features leverage advanced radio resource management technologies to automatically monitor and respond to changing RF conditions. When selecting an appropriate platform for a deployment, you should consider whether there is already an existing solution in place. If there is an existing MSM-based solution in use, it might be better to simply expand upon this existing platform, especially if the total number of APs is less than 800. If there is no existing solution, then base the decision on total number of APs. If you expect the solution to scale at some point to near 400 APs, it is best to start with a unified wired wireless access controller. Both platforms are compatible with most of the HP APs like the MSM-series. The unified controllers can also control the WA 2610, 2612, and 2620 series APs. Since we are focused on large-scale deployments, we'll focus your training on the unified solution. Let's review the access points that work with HP's unified access controllers. The HP MSM 425 and 430 provide 2 spatial streams and 3x3 MIMO capability. With channel bonding, this provides up to 300 megabits per second of theoretical data rate. The HP MSM 460, 466, and 466R provide 3 spatial streams with 3x3 MIMO for up to 450 megabits per second data rates. All are 802.11n capable dual radio APs. The 430, 460, and 466 feature internal Omni antennae for both 2.4 and 5 GHz radios. The 2.4 GHz has a 4 dBi of gain antenna, and the 5 GHz antenna has 7 dBi of gain. This is pretty smart design, huh? Remember how we spoke about how 2.4 GHz will travel farther through obstacles? The higher gain antenna will help the 5 GHz coverage pattern more closely match that of the lower gain 2.4 GHz antenna. The 425 also has internal antennas, 4 dBi gain for 2.4 GHz and 5 dBi gain for 5 GHz. It also includes 2 external antenna connectors for each radio, 4 total. The 466R is in a ruggedized NEMA-rated enclosure suitable for outdoor use, with 3 N-type connectors for each radio, 6 total. This AP does not include internal antennas. The HP MSM 560 and 525 are 802.11 AC capable 2 radio APs with up to 1.3 gigabits per second of theoretical throughput. The HP 517 unified wall jack integrates gigabit Ethernet ports, a dual-band 802.11 AC capable access point. The 417 is a similar wall jack unit with a 1 gigabit uplink and 3 100 megabit Ethernet ports, and an 802.11 BGN access point. HP's Intelligent Management Center, or IMC, is an SNMP-based management platform for your enterprise-class network. It provides a single pane of glass to manage all aspects of your network. It can manage thousands of wired routers and switches. It is a scalable platform that can be expanded through the addition of software modules. For example, the Wireless Services Manager module enables IMC to also manage HP wireless access controllers and HP FIT and Fat APs. This includes WLAN, AP, and radio configuration, as well as wireless topology monitoring and reporting. These features are not only available for HP products, IMC with WSM can also manage wired and wireless components from third-party vendors such as Cisco and Aruba. The IMC WSM platform offers a very rich set of features to manage ACs, APs, clients, radios, WLANs, and AP access ports. Wireless service alarms offer periodic polling, trap alarms, and syslog. Performance monitoring provides a real-time and historical trending for a myriad of wireless performance metrics. With topology and view management features, you can organize infrastructure devices by location and customize these views and visualize infrastructure connectivity. RF management creates heat maps so you can locate weak signals and adjust AP deployments accordingly. Spectrum Guard intelligently determines interferers such as microwave ovens, Bluetooth devices, cordless phones, and more. Wireless location management enables you to determine the location of your clients as well as rogue clients and APs. Wireless intrusion detection and prevention services help protect and mitigate against unauthorized APs and clients, ad hoc networks, and denial of service attacks. Network planning, reporting, and evaluation tools improve your awareness and ability to proactively manage WLAN systems. It is a very powerful tool. The User Access Manager, or UAM module, adds authentication, authorization, and accounting features, or AAA, to IMC. Authentication relates to who are you. If you provide correct username and password during authentication, you are allowed to connect. Authorization relates to what can you do. Now that you successfully authenticated, what resources will you be allowed to access? For example, A guest user may only be able to access the internet, while a corporate user may have access to most corporate resources. A high-level manager may have access to all corporate resources. Accounting relates to what did you do? This feature can track things like when did you log in, when did you log out, what did you access, what did you modify. UAM is also a key module for BYOD solutions. This adds additional criteria for authentication and authorization. For example, an employee that accesses the system via a corporate-supplied laptop may be granted access to most resources, but that same employee may be more restricted if they access the network with their personal smartphone or tablet device. These solutions can also perform a registration process that automatically configures a personal device for more secure access methods. Because the device is now using a more secure communications method, elevated access is automatically granted. BYOD solutions improve employee satisfaction by allowing personal device use without overburdening the IT department with configuration requests. Now that we've covered individual WLAN components, let's look at how we combine them all together into a functional system. A WLAN design that uses standalone Fat APs is most suitable for smaller deployments, often with a single switch and around 12 APs or less. Since they are Fat APs, each one must be individually managed and configured. You could deploy a centralized management platform, such as HP's IMC. However, this is not often feasible for a small deployment. You cannot justify the added expense just to manage 2 to 12 access points. Once configured and deployed, each AP is autonomously responsible for forwarding any wireless authentication frames to an authentication server and for forwarding data frames to and from each wireless client. In other words, these functions are distributed among the Fat APs. The advantage to this solution is mostly about cost savings. You merely need to purchase a few APs and maybe an Ethernet switch to connect them. The disadvantage is that it does not scale well. Imagine having to individually manage and configure a few hundred APs. This is why we deploy access controllers with a more centralized architecture. With this solution, you do not have to individually manage APs. You can manage and configure one or more access controllers, and the controller manages the APs. The ACs and IMC management platform are typically deployed near the core of the network. There may be smaller wiring closets throughout the facility, each with one or more access layer switches. APs are connected to these access layer switches. In a medium to large scale deployment, the added cost of the controller is negligible when compared to the vast improvements in scalability and manageability. Also, this solution is very flexible. You can configure the system so that FIT APs use distributed forwarding authentication, just like Fat APs. In some scenarios, a more centralized forwarding model may be appropriate. Let's explore these forwarding models in more detail. When you configure an SSID to use a distributed forwarding model, each AP receives any client authentication requests and forwards them directly to the authentication server, often hosted on the IMC platform, in the form of the UAM module we discussed earlier. As you can see, the access controller is not involved in authentication at all. Once the client successfully authenticates, it can begin to access network resources, such as a website on the internet. The end stations send a packet to some website. The source IP address is that assigned to the end station, as is the source MAC address. The destination IP address is the website. Since the client must access this site via its default gateway, the destination MAC address is this default gateway. The AP receives this wireless 802.11 frame and converts it to an Ethernet frame. Other than this layer 2 conversion and perhaps adding an 802.1q VLAN tag, nothing much changes about the frame. The source and destination MAC and IP address remain. This frame is forwarded to switch 2, the layer 2 switch. This switch forwards it on to switch 1, a layer 3 switch acting as the default gateway. Of course, the source and destination MAC addresses change as the IP packet gets re-encapsulated at each router hop. However, the layer 3 IP packet remains largely unchanged from original source, the endpoint, to ultimate destination, the internet site. This distributed forwarding approach is typically used for SSIDs that are reserved for corporate users. This is because there can be thousands of corporate users, but often only between 5 and 30 users per AP. Since each AP forwards all client frames directly to its destination, the solution is quite scalable. The access controller is not involved in any data forwarding operations, and so does not present a bottleneck to traffic flow. Some engineers may prefer to maintain a distributed data forwarding model while centralizing authentication. For any SSIDs configured with this approach, each AP forwards client authentication requests to the access controller. The access controller then forwards these requests to the authentication server. The server responds to the AC, which forwards them on to the AP and on down to the client. Success! You're authenticated. The AP forwards client data frames as before, directly toward the destination. In comparing central and distributed authentication, one could make valid arguments for either method. Bruce might say, with central authentication, you only have to configure the server to communicate with 1 or 2 controllers instead of hundreds of APs. However, says Gerline, I can configure my authentication server using a group feature to minimize this configuration task. Also, I have a bank of load-balanced authentication servers that can handle this load. Gerline may continue, with distributed authentication, frames take an optimal path directly from the AP to the server. But for centralized authentication, frames must first go to the AC and then to the server. Bruce counters, this is true, but the AC and IMC are connected to the same high-performance switch, so this issue is negligible. And back and forth we go. Some of these issues come down to personal preference and specific details of your environment. Either of these approaches will likely be just fine. With central access control, the client sends authentication and data frames to the AP as always. However, the AP wraps all 802.11 client frames inside another IP datagram. The source MAC and IP addresses of this new datagram are that of the AP itself, and the destination is the AC. Switch 1 and 2 are not aware of any WLAN client MAC or IP addresses, since all of this information is hidden inside the IP tunnel. All they see are the MAC and IP addresses of the AP and AC. The AC receives the packet and processes it internally. It strips off the outer IP packet, revealing the original Layer 2 802.11 frame and Layer 3 IP packet from the client. It is the controller that converts the 802.11 frame to an Ethernet frame and forwards it on to its destination. You may note that frames take a less optimal route, and the AC is in the data path of all frames from centrally switched SSIDs. Less scalable, you may think. This is true. However, this solution is for guests, and most organizations have relatively few guest users. Of much greater concern for guest users is security. All guest traffic is captive inside the tunnel between any AP and the AC. This means there's no need for security ACLs on any switch or router between the AP and AC. Centrally switched SSID traffic can only go to the AC. Once the AC receives it, it could be configured to send this frame out a separate logical interface. This interface could be connected to a separate internet connection that is only used for guest traffic. For these reasons, this is a very appropriate solution for guest users. Let's compare central and distributed forwarding. You may have configured all of your APs to support both the guest SSID and the corp SSID. A guest user connects to the guest SSID, which has been configured for centrally controlled forwarding. The client gets an IP address on the guest VLAN 20.2.2.2. As described, all client frames are tunneled between AP and AC. The AC receives the original 802.11 frame from the client, translates it into an Ethernet frame, and forwards it towards its destination. Therefore, SW1 is the first switch to see guest endpoint MAC addresses. It learns this MAC address on the port connected to AC1. From the wired switch's network perspective, this client can be reached via this port. Meanwhile, an employee connects to the corp SSID on the same AP. The corp SSID has been configured for distributed forwarding and has been mapped to VLAN 11. The client gets an IP address of 10.0.11.1. The AP receives 802.11 wireless frames from the client, translates them into Ethernet frames, and forwards them directly toward their destination. Therefore, SW2 learns the corporate client MAC address on the port connected to AP1. From the wired switch network's perspective, this client can be reached via this port. Our discussions in this session have focused on WLAN components, architecture, and deployment options. Now that we know about deploying these components, well, you probably know what's next, right? We want to learn how to actually configure this stuff. In the next session, you'll learn how to configure HP's converged wired wireless access controllers. This includes initial configuration and AP control, as well as configuring SSIDs for client access and more.